Welcome back to the channel. We start our lecture number 3 on Quantum Electrodynamics QED. Quantum electrodynamics also provides a framework for understanding how information is carried by light and how energy is transferred at the smallest scales. Every time light interacts with matter, whether it is absorbed, reflected, or transmitted, a quantum process is taking place. In QED terms, this means photons are being exchanged between the electromagnetic field and charged particles such as electrons. These exchanges determine how much energy is transferred and in what direction momentum flows. Even something as ordinary as the color of an object is connected to these microscopic interactions, because color depends on which frequencies of light are absorbed and which are reflected, and that behavior depends on how photons interact with electrons in the material. One of the fascinating outcomes of QED is its explanation of why light sometimes behaves like a stream of particles and sometimes like a wave. In the quantum field picture, light is fundamentally a field, and photons are quantized excitations of that field. When we observe interference or diffraction, we are seeing the wave-like aspect of the field. When we detect individual photons striking a detector, we are seeing the particle-like aspect. QED unifies these two pictures by showing that they are not separate descriptions, but different ways of probing the same underlying structure. The apparent contradiction between waves and particles dissolves into a single, coherent framework. The role of symmetry in QED cannot be overstated. The electromagnetic interaction is governed by a principle known as gauge invariance, which means that certain changes in the mathematical description of the electromagnetic field do not affect observable quantities. This symmetry is deeply connected to the conservation of electric charge. In other words, the fact that electric charge is conserved in all known processes is not just an empirical rule, but a consequence of the structure of the theory itself. This insight has influenced the development of many other physical theories, showing how conservation laws can emerge from symmetries. QED also reshaped how physicists think about the vacuum. Instead of viewing empty space as truly empty, the theory shows that it is a dynamic medium filled with fluctuating fields. These fluctuations can influence the motion of particles and the propagation of light. For example, two uncharged metal plates placed very close together in a vacuum experience a tiny attractive force due to changes in the vacuum fluctuations between them. This phenomenon illustrates how the properties of empty space itself can have observable consequences, a concept that would have seemed almost mystical before the development of quantum field theory. Another insight provided by QED is that particles can influence each other even when they are not in direct contact. The exchange of virtual photons allows charged particles to interact across empty space, creating what we perceive as forces. This picture removes the need for action at a distance and replaces it with local interactions mediated by fields. Every force becomes a sequence of microscopic events in which particles emit and absorb quanta of a field. This local field-based description is more compatible with the principles of relativity and provides a clearer understanding of how influences propagate through space. In the laboratory, QED has guided the interpretation of countless experiments. High-precision spectroscopy, scattering experiments, and measurements of magnetic properties all rely on QED calculations to separate electromagnetic effects from other influences. When experimental results agree with these calculations, confidence in the theory is strengthened. When small discrepancies appear, they become opportunities to search for new physics. This makes QED not only a theory of known phenomena, but also a tool for discovery. The computational techniques developed for QED have had wide-ranging applications. Methods for handling infinities, organizing perturbative expansions, and interpreting diagrams have been adapted to other areas of physics. Even in fields that do not directly involve electromagnetism, similar mathematical structures appear, and the lessons learned from QED prove useful. This transfer of ideas across different domains shows how progress in one area of science can stimulate advances in others. QED also encourages a particular attitude toward physical theories, one that balances skepticism with trust in evidence. The early difficulties with infinities might have led physicists to abandon quantum field theory altogether. Instead, they persisted, guided by experimental results and by the conviction that a deeper understanding was possible. This persistence paid off in the form of a theory that not only works, but works with extraordinary precision. The history of QED thus serves as a reminder that scientific problems often require patience and creativity to solve. The way QED treats time is also noteworthy. In calculations, processes are often represented as happening over intervals of time that are too short to be directly observed. Virtual particles can appear and disappear within these intervals, contributing to the overall probability of an event. This suggests that the microscopic world operates on timescales and distances far removed from everyday experience. Yet the cumulative effect of these fleeting processes shapes the behavior of matter and radiation on macroscopic scales. QED's influence on our understanding of causality is subtle but important. While the theory respects the relativistic limit that no signal can travel faster than light, its mathematical expressions sometimes include contributions that look like particles moving backward in time. These features arise from the need to maintain consistency with relativity and quantum mechanics simultaneously. They do not imply that time travel occurs in reality, but they show that our intuitive notions of cause and effect must be refined when dealing with quantum processes. In practical applications, the principles of QED are often hidden beneath simpler formulas. Engineers designing electronic devices or optical systems rarely use full quantum field theory. Instead, they rely on approximations that capture the essential physics without the complexity of the full theory. However, the reliability of these approximations ultimately rests on the deeper framework provided by QED. It acts as a foundation upon which more accessible models are built. Another remarkable feature of QED is its universality. The same interaction rules apply whether we are studying electrons in an atom, particles in a collider, or radiation traveling through space. This universality reflects the fact that the electromagnetic interaction is one of the fundamental forces of nature, operating at all scales. By providing a single description that applies in such diverse contexts, QED demonstrates the power of unifying principles in physics. The success of QED has also influenced how physicists evaluate new theories. Any proposed extension or replacement of QED must reproduce its predictions in the appropriate regime. This sets a high standard for theoretical innovation. New ideas must not only explain phenomena that QED cannot, but also agree with the vast body of experimental data that QED already accounts for. In this way, QED serves as both a guide and a constraint in the search for deeper laws. From an educational perspective, learning about QED can be transformative. It introduces students to a world in which fields, particles, and probabilities replace the familiar objects and forces of classical physics. This shift can be challenging, but it also opens up new ways of thinking about nature. It encourages students to see physical laws as abstract structures that can be expressed mathematically and tested experimentally rather than as simple extensions of everyday experience. The legacy of QED is not only scientific but also cultural. It represents a triumph of human intellect over a problem that once seemed insurmountable. It shows how collaboration, debate, and the exchange of ideas can lead to breakthroughs. The story of its development involves multiple contributors, each bringing different insights and techniques. Together, they built a theory that has reshaped our understanding of the physical world. QED also highlights the role of imagination in science. To conceive of particles exchanging virtual quanta or of empty space filled with fluctuating fields requires a willingness to go beyond common sense. Yet these imaginative constructs are not arbitrary. They are disciplined by mathematics and by experimental evidence. This combination of creative thinking and rigorous testing is a defining feature of modern physics. As technology advances, new tests of QED become possible. Experiments with ultra-intense lasers, high-energy accelerators, and highly controlled atomic systems allow physicists to probe regimes where QED effects are especially pronounced. These experiments not only verify existing predictions, but also explore areas where deviations might appear. Such deviations could signal new physics and lead to further refinement of our theories. In a broader sense, QED exemplifies how scientific knowledge grows. It did not emerge fully formed but evolved through a series of partial insights and corrections. Early theories captured some aspects of electromagnetic interaction but failed in others. QED built on these earlier ideas, resolving contradictions and extending their range of validity. This evolutionary process is characteristic of science as a whole, showing how understanding deepens over time through a combination of continuity and change. The conceptual framework of QED also encourages a holistic view of physical phenomena. Instead of treating light, electricity, and magnetism as separate topics, it shows that they are manifestations of a single interaction. This unified perspective helps to reveal connections between different areas of physics and to simplify the overall picture of how the universe works. In reflecting on quantum electrodynamics, we see a theory that is both precise and profound. It captures the fine details of how particles interact, while also pointing toward deeper principles such as symmetry and field dynamics. It reveals that what we perceive as forces and particles are aspects of a more fundamental structure, one that operates according to probabilistic rules and respects the constraints of relativity. Ultimately, QED teaches us that understanding the universe requires both humility and ambition. Humility because our intuitions are often inadequate guides to the microscopic world. Ambition because with the right tools and ideas we can uncover laws that govern even the most elusive processes. The theory stands as a reminder that nature, however strange, can be understood through careful observation, creative reasoning, and mathematical clarity. By continuing to study and apply QED, physicists deepen their grasp of the electromagnetic interaction and refine the methods used to explore other forces. The theory remains a living part of science, not just a historical achievement. It continues to shape research, inspire new experiments, and inform our picture of reality. In doing so, it upholds the central goal of physics, to describe the natural world in a way that is both accurate and illuminating. Quantum electrodynamics also deepens our understanding of how limits arise in physical theories. Although QED is extraordinarily accurate, it is known that it cannot be the final description of nature. At very high energies, new effects are expected to appear, and other interactions become important. This reminds us that every theory has a domain in which it works well and a boundary beyond which it must be replaced or extended. QED is a perfect example of a theory that is extremely powerful within its proper range, even if it is not the ultimate theory of everything. One of the ways QED teaches us about limits is through the concept of scale. At ordinary energies, the electromagnetic interaction appears simple and stable. However, when we probe much higher energies, the effective strength of the interaction changes slightly. This happens because the vacuum itself responds differently, depending on the energy of the process being studied. The cloud of virtual particles around a charge behaves in a way that depends on how closely we look. This idea that physical quantities depend on scale has become central in modern physics and plays a key role in many other theories beyond QED. Another important lesson from QED is the role of consistency. The theory is built so that it respects both quantum mechanics and special relativity. This was not a trivial achievement, because these two frameworks were originally developed for different purposes. Combining them required new mathematical structures and new ways of thinking about particles and fields. QED shows that it is possible to unify different principles into a coherent whole, provided one is willing to rethink basic concepts such as particle motion and interaction. The notion of interaction in QED is also more subtle than in classical physics. Instead of forces acting continuously, interactions are described as discrete events where quanta are exchanged. These events are governed by probabilities rather than certainties. This leads to a picture of nature in which outcomes are not predetermined, but emerge from the interplay of many possible processes. Such a view challenges classical determinism and suggests that unpredictability is not merely a practical limitation, but a fundamental feature of the universe. QED also illuminates the relationship between theory and measurement. In many areas of physics, measurements are interpreted using classical concepts such as position, momentum, and force. In QED, these concepts must be redefined in terms of operators and probability distributions. The act of measurement itself becomes part of the theoretical description. This means that what we observe is inseparable from how we observe it. The theory does not describe an objective reality independent of observation, but a reality that is revealed through specific experimental arrangements. The idea that particles can be created and destroyed is another profound contribution of QED. In classical physics, particles are permanent objects that persist over time. In quantum field theory, particles can appear and disappear as long as conservation laws are respected. A photon can turn into an electron-positron pair, and that pair can later annihilate back into photons. These processes are not rare exceptions. They are integral to the theory. This view of matter as something that can transform into energy and back again reflects a deeper unity between what we traditionally call matter and radiation. QED also offers insights into why certain processes are common and others are rare. The probability of a given interaction depends on how strongly the relevant fields are coupled and on how many intermediate steps are involved. Simple processes, such as the emission of a single photon by an electron, are relatively likely. More complex processes, involving multiple photons or particle loops, are much less likely. This hierarchy of probabilities helps explain why the world appears stable and predictable at large scales, even though it is governed by probabilistic rules at small scales. The theory also helps us understand the role of conservation laws in shaping physical processes. Energy, momentum, and charge must be conserved in every interaction described by QED. These conservation laws restrict which processes can occur and which cannot. For example, a single photon cannot spontaneously turn into an electron-positron pair in empty space, because such a process would violate energy and momentum conservation. Only in the presence of another particle or a strong field can such a transformation occur. In this way, QED shows how abstract principles translate into concrete restrictions on physical behavior. Another theme that emerges from QED is the importance of symmetry breaking. While the fundamental equations of the theory are highly symmetric, the states we observe in nature often do not display these symmetries in an obvious way. This distinction between the symmetry of the laws and the asymmetry of particular solutions is a powerful idea that extends beyond electromagnetism. It suggests that the complexity of the world arises not from complicated laws but from the many ways simple laws can be realized. QED has also influenced how scientists think about the connection between microscopic and macroscopic phenomena. The theory operates at the level of individual particles and fields, yet its consequences can be observed in bulk properties of matter, such as electrical conductivity and optical behavior. This shows that large-scale phenomena can often be traced back to quantum interactions at much smaller scales. It provides a bridge between fundamental physics and the properties of everyday materials. In exploring QED, physicists have developed a rich set of conceptual tools, including ideas about virtual particles, renormalization, and gauge invariance. These tools have proven useful far beyond their original context. They have been adapted to describe other forces and to analyze systems in which collective behavior emerges from many interacting components. The influence of QED thus extends into many branches of theoretical and experimental physics. QED also underscores the importance of experimental precision. Many of its most striking predictions involve extremely small effects that can only be detected with advanced instruments. This has driven the development of highly sensitive measurement techniques and has raised the standards for what counts as a meaningful test of a theory. The close agreement between QED calculations and experimental data demonstrates how far measurement technology has advanced and how deeply theory and experiment are intertwined. The theory further teaches us about the role of approximation in scientific knowledge. Although QED is formulated in exact mathematical terms, most practical calculations rely on approximations. These approximations are carefully controlled and justified by the smallness of the electromagnetic coupling. This shows that scientific understanding does not require exact solutions in every case. It requires methods for estimating effects and assessing their reliability. The success of QED illustrates how approximate reasoning can yield extremely accurate results when guided by a sound theoretical framework. Another philosophical lesson of QED is that reality may be best described not in terms of objects but in terms of processes. Instead of focusing on particles as enduring entities, the theory emphasizes interactions and transformations. Particles appear as temporary manifestations of underlying fields, and their properties depend on how they interact with their environment. This process-oriented view aligns with the probabilistic nature of quantum theory and suggests a dynamic picture of the universe at its most fundamental level. As scientists continue to probe the frontiers of physics, QED remains a reference point for what a successful theory looks like. It combines mathematical consistency, physical insight, and experimental verification in a way that few other theories have matched. Any new framework that aims to describe fundamental interactions must be able to reproduce the achievements of QED while also extending beyond them. The enduring relevance of QED lies in its balance between abstraction and application. It is abstract in its use of fields, operators, and symmetries, yet it is directly connected to measurable quantities such as scattering angles, energy levels, and magnetic moments. This balance makes it both intellectually satisfying and practically useful. It shows that a theory can be deeply mathematical without losing contact with physical reality. In contemplating quantum electrodynamics, we are reminded that the pursuit of knowledge often leads to unexpected places. What began as an attempt to understand the interaction between light and electrons led to a new conception of empty space, a new understanding of forces, and a new mathematical framework for describing nature. These developments were not planned in advance. They emerged from the effort to solve specific problems. This illustrates how progress in science often comes from following questions wherever they lead. QED also highlights the creative aspect of theoretical physics. The development of new concepts and methods required imagination, as well as logical rigor. Physicists had to invent ways of thinking about phenomena that could not be directly observed, guided only by experimental clues and mathematical consistency. This creative dimension is sometimes overlooked, but it is essential to the advancement of science. By studying QED, we gain insight into how complex patterns can arise from simple rules. The exchange of photons between charged particles, governed by a single interaction principle, leads to the vast array of electromagnetic phenomena we observe. This suggests that the richness of the universe may be rooted in a small number of fundamental interactions, each with its own distinctive character. Ultimately, quantum electrodynamics invites us to view the universe as an interconnected web of interactions rather than a collection of isolated objects. Light and matter are not separate realms but aspects of a single unified framework. The forces that shape atoms and molecules are the same forces that govern the behavior of radiation across the cosmos. In revealing this unity, QE deepens our appreciation of the coherence of natural law. Through its concepts and methods, QED continues to shape our understanding of the physical world. It challenges us to rethink familiar ideas, to accept probability as fundamental, and to see empty space as active rather than inert. It shows that even the simplest interactions can have profound implications when examined closely. In this way, QED stands as both a scientific achievement and a philosophical milestone, marking a new stage in humanity's effort to comprehend the nature of reality.